is that it's important that we understand the impact that the data type has on the analysis that we're going to do. So, for instance, when I am comparing two groups in relation to some numerical variable. So, for instance, let's say I'm looking at males versus females, and I want to compare them in the population. I want to compare males in the population to females in the population with regard to, let's say, scores on an aptitude test. Okay, or some other like motor test, aptitude test, whatever. And I want to see if there's a gender difference between the average for the male population and the average for the female population. Well, I'm never really going to know unless I test every male in the population. Let's say my population is New York City, right? Unless I test every male in New York City and every female in New York City, I'll never know what the true mean is on this test for all the males, or what the true mean for females is on this test. So I won't know if they're equal or if they're not equal, if the means are equal to one another. And there's no difference between the two groups, or there is a difference between the two groups. So in this case, I have two variables that I'm working with. I have gender. Gender is one variable, right? And one value we have for gender is male. The other value we have for gender is female. So it happens to be binomial. It happens to has two values. And the other value I have is the test score. And the test score is numerical. So when I am comparing numerical variables, right, the test that I am going to be using is either a t-test or analysis of variance, ANOVA. The t-test is used when we're comparing two means to one another. Analysis of variance is when we're comparing three means or more. So if we're comparing males versus females, we're going to use the t-test. If we're comparing different ethnicities, okay, and we might say white, black, Puerto Rican, or Hispanic, let's say Hispanic, Pacific Islander, and so on and so forth. If I have four ethnic groups, I'm comparing the means of whites to blacks and Hispanics to Pacific Islander. I will be looking to compare four means: the means for whites, the means for blacks, the means for Hispanics, the means for Pacific Islanders. Right? Those are four means I'm looking to compare. In that case, I use analysis of variance. The reason why I use analysis of variance is because t-test is only designed to compare two means at a time. So if I wanted to do these comparisons, I would have to run a t-test comparing whites to blacks, whites to Hispanic, whites to Pacific Islanders, blacks to Hispanic, blacks to Pacific Islanders, and Hispanics to Pacific Islanders. I'd have to do the test 6 times in order to compare all of these. And each time I do the test, my acceptable level of error typically is 5%. Well, if I do the test 6 times, I increase the chance that I'm going to be wrong if I at least in one of my analyses, right? Because I just keep repeating it over and over again. Not to mention the fact it's going to be, if we have even more groups, it's going to be pretty tedious to do this over and over and over again. So we have a separate analysis called analysis of variance. If you look at the video that I put online that steps through doing the analysis of variance manually and then doing it with SPSS, I think you'll get a pretty good idea of how that works for you. I took a small data set of a nominal variable that has 3 values in it. They happen to be names, and numerical data that goes with them. Okay, so you might want to take a look at that if you review that if you're still having problems with it. Then finally, the last test I'm interested in covering today is chi-square and odds ratio. Odds ratio also and relative risk, which is kind of similar to relative risk. With this particular test, we use this particular test for comparing categorical variables, right? So for instance, maybe we're interested in knowing if there's an association between gender and being left-handed, right? So those are both categorical variables. Gender is male or female, and left-handed, again, happens to be 2 by 2, doesn't have to be 2 by 2. Left-handed is left-handed or right-handed, or it could be left-handed or right-handed, or neither. Okay? So we can analyze this to determine whether there's an association between gender and left-handedness, or if there's no association. So that's chi-square. Chi-square, we're working with 2 categorical variables, and the t-test, we're working with the means of 2 variables, a numerical variable and categorical variable. And analysis of variance, we're working with categorical variable with at least 3 or more values, and a numerical variable, the means of those 3 different groups. So I'm going to try several different approaches here using SPSS. Okay, let's get this out of the way. So I'm going to start with the data files that we had here for the t-test exercise. And I'm going to look at, for instance, I'm going to look, number 1, at a single sample t-test. Okay, and here's our data from that single sample t-test. And I see my data, my variable name is X, right? Could be anything. I could change that, for instance. I could change that to, let's see, X is numbers are pretty small numbers. Let me call X shoe size. For instance, shoe size. I can't put a space in there for the variable name, right? So I can put in here shoe size, or shoe size for bowling. I've been bowling in ages. And I can let SPSS know that if I take a look at this, that's a numerical variable, right? So I have a single variable. I don't have 2 variables, only 1 variable, and that variable is named shoe size. So I'm going to take a look at the data that I have, right? Real big shoes, it must be NBA, right? Because they have real big shoe sizes here. And I'm going to say to myself, I want to know whether the shoe size for the population that I drew this sample from, there's 9 people that have been randomly chosen and their shoe size measured. I want to know if the shoe size of basketball players is different than the shoe size of football players. As it happens, I'm going to make believe that I know the mean shoe size for all football players. I'm going to take the shoe size for basketball players, and I'm going to say analyze the descriptive statistics, descriptives, and I'm going to move that in here, and I'm going to ask it to tell me the average shoe size for basketball players. And it turns out like the average shoe size is around 12, it's 11.78 for our sample. I don't know what the mean is for the entire population in the NBA, but I know my random sample of 9 basketball players happens to be a little under 12 inches. Well, okay, so I happen to know that the true shoe size for all football players is 12.5. So I want to know whether I can say with 95% certainty, less than 5% chance of being wrong, that the average shoe size for NBA players is different than the average shoe size for NFL players. Okay, so I'm going to open this up again, and I'm going to write that down. I'm going to write that down in the form of hypothesis. Okay, because this is, after all, called hypothesis testing. So I'm going to say that I know mu for NFL. I don't know mu for NBA, right? However, I know my sample of size 9. My sample of size 9, the mean is equal to 11 point. I missed it. Let's see. Where to go? I have to go to the output window. Okay. Is 11.78. Okay. Is 11.78. Okay. So I'm never going to know. I know what this is, but I'm never going to know what this. This is always going to be a mystery to me because I don't have the opportunity to measure all the NBA players, and I can only know what it might be based on my mean of my sample of size known. So I want to compare the two means of these two groups. And one I know the mean, and the other I only know what the sample mean is. Okay, but my hypothesis is always about the means, the true means of the populations. So my start for my hypothesis is my null hypothesis, my starting or equal hypothesis. And my starting hypothesis is that the mean shoe size for in the NFL is equal to the mean shoe size in the NBA, or the other way around. My alternative hypothesis, which is what we're really trying to prove here, is mu for the NFL is not equal to the mean for the NBA. Okay, so that's my alternative hypothesis, right? So in order to prove that, I have to show that the difference between 11.8 based on 0.78 based on my sample is different enough from the NFL, which I said was 12.5, right? Is different enough that I can be 95% certain that the true means are really, the true means, which is unknown in this one, right? There's the X bar, that the true means are really different with that level of certainty. In other words, alpha equals 0.05, or in other words, I would only get this extreme of difference between the two means, including the sample and the true mean for the NBA, if there's less than 5% chance that I would get this extreme of difference if the null hypothesis were true. So I can go ahead and then reject the null hypothesis and accept the alternative hypothesis. So I'm going to do this using SPSS. Okay, so the way that I do that, I'm going to take my sample and I'm going to say analyze. Now I'm comparing means. So I'm going to go down to compare means. And in this case, I know the mean of one group. I don't know the mean of the other. So I'm only taking a single sample. If I had two samples here, in other words, if I didn't know the mean of either group, I had to take a sample from the NBA, sample from the NFL, I would use independent samples or two samples t-test. So I'm going to take a one sample t-test. So I'm going to move the shoe size for, I should have said for the NBA, I said for bowling. So I changed my mind because it seemed more plausible. So I'm going to move that into there. But that's a X bar. That is a sample mean. I'm going to put in, for the test value, I'm going to put in 12.5, which is the known mean for all the players in the NBA. Okay, so I think that's all we need, right? We'll get a confidence interval, we'll calculate the differences and so on and so forth, and it'll calculate a t-score for us. So I'm going to click OK. Output window is going to come up in SPSS. And in this output window, I can see a couple of things. Number one, my sample size is 9. My mean is 11.78. My standard deviation of my sample of 9 people is 1.98. And I take my standard deviation, use it in place of sigma, the population standard deviation, and divide by the square root of the sample size, which is 9, square root of 9, which is 3, divide that by 3, and I get a standard error of 0.662. So that standard error, I want to know if I'm enough standard errors apart between 11.78 and 12.5 to reject the null hypothesis. So the way I would calculate my t-score would be my t-value, the number of standard errors apart that these two values are, is that it's going to be equal to X bar, 11.78, minus the mean, 12.5, over 6.62. And that result turns out to be 11.78, and 12.5 is about 3/4 divided by 0.66. It's going to be a little over 1. And in fact, here's our t-value here, 1.09. That's our t-score. Okay, it doesn't matter if it's positive or negative. That just is a matter of which I put first, the 11.78 or the 12.5. Doesn't matter. The magnitude, the size of it is what matters. As it happens, it's 8 degrees of freedom. We know that the degrees of freedom is equal to the sample size minus 1. So I could actually, right now, I could look up the t-table and see what the value of t, how many standard errors apart that I would need these to be to reject the null hypothesis. So for 8 degrees of freedom, whoops, for 8 degrees of freedom, don't need that. For 8 degrees of freedom, I'll blow this up just a little bit. For 8 degrees of freedom, I would need a t-score of 2.306 or larger. See, 95% confidence, 0.025, 2.5% in each of the tails, the right tail and the left tail, which is 5%, and 95% confidence. So this would be 2.306. That's the t-value I would have to exceed to reject the null hypothesis. 12.5 was the mean for the other group I'm comparing our sample group to. In other words, players in the NBA, and I know that's the true mean for all players in the NBA because they're all measured, right? The NFL rather. The NBA, we only had a sample of nine players. Okay, so I need to exceed a t-score of 2.306 to be able to say with 95% certainty that the two means are really different. Okay, so now if I go back and take a look, what is my t-score? Well, it's only 1.09. So I have not exceeded the critical value of t that I need to exceed to reject the null hypothesis. Okay, so, and you'll notice that I also have SPSS calculates for me a significance or a p-value. You can call this a p-value, you can call this a significance, but this is the probability that you would get this big an outcome, this large a difference, if the null hypothesis were true. In other words, there's a 30% chance I would be wrong if I reject the null hypothesis, because there's a 30% chance I could get this outcome when the null hypothesis was true. You get this big a difference, 11.78 versus 12.5, if the null hypothesis happened to be true. So in this case, I failed to reject the null hypothesis. Reject the null hypothesis. I don't accept the null hypothesis because I haven't proved the null hypothesis true. All I've done is I don't have enough evidence to be able to say I can reject it, right? So I can't say it's true, but I can't reject it either. So ideally, what I would have preferred is to be able to reject the null hypothesis, accept the alternative, and say that at least to this level of certainty that I want that I have successfully proven less than 5%, not proven, but less than 5% chance of being wrong. I have shown that there is a difference in the average shoe size between players in the NFL and players in the NBA. So let me go back here, and I'm going to do this again. Okay, and this time I am going to use 13.5 as a shoe size. From football players, they eat a lot, you know, so they have big feet. So let me go back here, except this time I'm going to change this because I think I may have confused you a bit. Can I get in there? Let's see if I can change. There we go. NFL, NBA players. Oops, excuse me. Okay, so now I'm going to give this a try again. Say analyze, compare means, one sample t-test. Remember, it's only one sample being taken here. And this time, I'm going to say the test value, the mean of the group that I'm comparing it to, NBA players, has a shoe size of 13.5. I'm going to click OK, and I'm going to get a result for my t-test now. Okay, so let's see what my t-test says. So 11.78 standard deviation, standard error is the same. 11.78 minus 13.5. right, is going to be a bit more, isn't it? It's going to be a t-score of 2.601. You remember what the critical value of t was for 8 degrees of freedom? Sample size 9 and 8 degrees of freedom. It was 2.306, I believe. So in this case, I've exceeded my critical value of t. The two means are far enough apart that I would expect to get this big a difference between the two means, even with the small sample size, less than 5% of the time if the null hypothesis were true. So therefore, I can reject the null hypothesis and have less than a 5% chance of being wrong if I reject the null hypothesis. Now, SPSS very conveniently not only calculates the t-value for us, so I can look it up against the table, but it also calculates the probability you would get this extreme of value if the null difference between these two means, if the null hypothesis were true. And in this case, it comes out to be 3.2%, 0.032, which is less than 0.05. Confirmation that we've exceeded the critical value of t. So either one of these, the fact that this is bigger than 2.306 and the fact that this is less than 0.05, both confirm that they're different enough that I can reject the null hypothesis and accept the alternative hypothesis. Are you guys comfortable with that? I'll pause for a moment. Okay, at least some of you are comfortable with that, right? Okay, hopefully if you need to, you can go back and take another look at this as well. Okay, so I'm going to do another example, except this example, and I'm going to go back to our group, this group here, and I'm going to open up this 2-sample t-test. Okay, and I'm going to repeat this with another quick. I'm going to repeat this quickly with another data set when I get done with this. Okay. See if SPSS cooperates. Let's see if it's open already. Nope, not open yet. Oh, there we go. That's opening a new version of SPSS. Opening up another version of SPSS. I've been clicking on it. I hope it doesn't open more than one. What I can do about this to speed things up. Oh my goodness, look at this. Let me close some of these. Hopefully I'll only have one version of SPS open when I'm done. And there we go, here we go. Okay, and this time I'm going to do this a little bit differently. I'm going to say open data, and I'm going to navigate to that folder which is on my desktop, which is that it's already there, data files. So I'm going to open up this sample, 2-sample t-test. There we go. Okay, so now in this one, I have two groups. This value might be a test score, for instance, and this value is a test score. I'm going to change that so that it makes a little bit more sense. I'm going to call that test, oops. Test score. I'll give that variable name test score. Okay, and then here in label, I'll explain this a little bit more. I'm going to say that's an aptitude test score. And over here for gender, I will put, I'll just put gender. I'll just repeat what is the name of the variable. So now on my tables, any tables and charts that come out of SPSS, instead of using test score like that, no spaces, and gender, instead of using the variable names, it will use gender and aptitude score on my tables and charts. A little bit more descriptive than just this kind of goofy abbreviated version of what these values are. Okay, so now in this case, if I go back to my data view, I have two variables here. I have the test score itself, which is a numerical variable, and I have gender. Gender happens to have two values, male and female. I can just quickly say, if I go over here to view, I can turn the value labels on, and you can see that gender is really 1 and 2 is really what data is in here. But if you go to the variable view, you
Jonathan,
can see under the values for gender.
Jonathan,
If I click into the values group, you can see that we've defined for SPSS that 1
Jonathan.
equals female and 2 equals male. Okay, that's how SPSS knows that 1 and 2
That's all right.
really
That's all right.
turn on the value labels. 1 and 2 actually represent male and female. So I have 2 groups. So, thank you for reminding me about the muting. Okay, if the other student doesn't do it, sometimes when you log on, it ignores my mute command, and the student has to realize to mute themselves, or either that, if I'm aware of it, I can mute it from here. So thank you for that heads up. So at any rate, so I'm going to now compare these 2 groups. Okay, there's 2 samples here. I've taken a sample of males and a sample of females. You know what I'll do first? Since I have SPSS available to me, first I'm going to go to Analyze, Descriptive Statistics, Explore, and I've noticed if well, actually, first, before I do that, just to point out how this works, Descriptive Statistics, Descriptives, and I can tell that I'm interested in the descriptive statistics for the aptitude test scores, the means for the aptitude test scores. So I'm going to click OK, and SPSS will calculate the mean for the test scores for me. And the average test score was 8.78, and there were 18 subjects, and that's the average, and that's the, well, unfortunately, it gave me the average test score, but for all of the males and females combined. So I'm really more interested in comparing the male test scores to the female test scores. So I'm going to go back, Analyze Descriptive Statistics, and I'm going to go beyond descriptives to Explore. And in Explore, now I have the opportunity to move the aptitude test score, in other words, when I'm finding the actual mean of the numerical variable. Notice there's like a little ruler there to indicate it's a scalar variable. And I'm going to move gender into the factor list. That tells SPSS, I don't want just the average test scores for everybody. I want the average test scores broken up by gender. Okay, so I can click into statistics, and it's going to do descriptive statistics, 95% confidence interval scores. That's just fine. That's acceptable to me. And it's going to create some it's going to create, so for instance, if I want histograms, I can check off histograms. If I don't like stem and leaf plots, I can turn that off. But it's automatically going to create side-by-side box plots for me. Okay, and I think you guys probably remember doing that, I believe, on the first homework. So now, when I click OK, I should get both side-by-side box plots and statistics for the means, standard deviations, etc., for males and females on this test scores for separately from one another. So let's click OK. Let's see what my output table looks like. Here we go. Here's my output table. So you can see that there were 9 females, 9 males, no missing values. And the mean for females was 10. The mean for males was 7.56. Females appear to have scored considerably better than males did on this exam, on this aptitude test. The only problem I have now is that difference, 7.56 and 10, in this small sample of 9 people each from these populations, is that small sample enough for me to say with 95% certainty alpha equals a 0.05? In other words, alpha 0.05, the probability we'd get this big a difference if the null hypothesis was true, the means of the 2 populations are the same, is less than 5% is what I'm aiming for. Okay, so 7.56, and look, we have standard error for this group, and standard error, and we have standard deviation for females is 2.73. Standard deviation for males is 1.98. You know, standard deviations are a bit different, but one is not double the other. So normally, I would have to make a decision now about whether to consider these 2 standard deviations different or the same. If I can say that they're not different, that they're similar enough, in other words, one is not double the other. If I can say that they're close enough, I can then combine the 18 scores to calculate a single standard deviation and a single standard error to use in my calculation for a t-score. My t-score is going to be equal to the difference between the two means, x bar 1 minus x bar 2. There's no means here because I only know x bars, over the standard error based on the standard deviation of all of them, not just two of them. So I would have to make a judgment about whether I can pool those because they're similar or not pool them. And in SPSS is going to calculate it with both assumptions. I would, if I were doing this manually using Excel, I would use the formulas for, and you have the formula sheet from that particular evening's work, the formula sheet for equal variances as opposed to unequal variance. On the other hand, if this had been 4.7 and this was 1.9, I would use the formulas for unequal variances. But SPSS is going to work this out for us. So now that I have a rough idea what these statistics for two groups look like, the descriptive statistics, I'm going to go to Analyze. I'm going to go to Compare Means. I'm still comparing means here, except this time it's not one sample. I took two samples. The two samples were independent. There's one group that's a random sample of females, another group random sample of males. So they're independent samples. I'm going to click that. And again, I'm going to move my aptitude score into the test variable, right? That's my numerical variable, what I'm going to calculate means of. And I'm going to move gender into the grouping variable so that the t-test will look for the difference between the two means. Now, SPSS requires you to define the two means, what the values are for the two means. And I believe it's 1 and 2. I think that's what we saw when we did this. 1 represents female, 2 represents male. It's an extra step. You would think SPSS would be able to figure this out for itself since there's only 2 values in that group, but you do have to put that in. Okay, so now it understands that we want to break this up into males and females. In other words, 1 and 2. So I'm going to click OK, and SPSS will do this test for us. Okay, let's take a look what happens. So now I could go to my, in this test, I could go to my t-table to look for a critical value of t to compare the value of t that I calculate. But SPSS is doing that for me. So I'm going to first look at my samples. Indeed, 10 is the mean for females, 7.6 is the mean for the male sample. Okay, and our standard deviations and standard errors. Okay, so now SPSS calculates the standard error it's going to use and figures out how many standard errors apart, what t is equal to. So this part of it here, this first part, Levine's test for quality of variances, this part of it here is not part of the actual t-test. The actual t-test starts here with t and goes to the left, right? So this t-test starts here. This part is to decide whether the variances are different enough to assume equal variances or not assume equal variances. Do you guys remember what I said about assuming equal variances in this particular case? Since the standard deviations were not, one wasn't double the other, I would just assume equal variances. Well, in fact, that means I would stick with the top row. Well, this calculation, test for equality of variance, does exactly that. It does it mathematically. It doesn't do it just by glancing at it and saying one is double the other. It actually calculates the probabilities for this. Again, like many other things that we do, the null hypothesis is, in other words, the default hypothesis is that equal variances are assumed. So unless the probability that this is wrong is less than 5%, that this is not right, is less than 5%, I'm going to stick with the top row. So Levine's test for equality of variance comes out with a statistic value of 1.456 with a significance of probability that I would be wrong if I reject equal variances and use equal variances not assumed, is 25, almost 25% chance that I would be wrong if I did that. So I can't reject this, so I have to use the top row instead of the bottom row. Often it's not going to make much difference to you. Right? It's not going to impact your final conclusion. Okay, so let's see what our t-score was. Our t-score was 2.144, 16 degrees of freedom. Remember that our degrees of freedom, when the degrees of freedom were 8, now this degrees of freedom is equal to n1 plus n2, 2 sample sizes minus 2. So 9 people and 9 people is 18 minus 2 is 16. Degrees of freedom when you assume unequal variances is a complicated calculation. Turns out to be a very odd number, but that happens to be what it is. But for 16, we know that for a smaller sample size, 9, my degrees of freedom was 8. This is 9. We know before it was 2.3. Let's see what it is for 16. Okay, so 16 degrees of freedom. Our t critical is 2.12. Before we reject the null hypothesis, we want our calculated t value to be bigger than the critical value, 2.12. So I'm going to go back here. Okay, let's see what we got in our output here. Okay, in our output, our t value was 2.184, which is greater than 2.12. So my t-score is big enough compared to the critical values of t on the table, big enough for me to reject the null hypothesis, mu for males is equal to mu for females, and accept the alternative hypothesis, mu for males is not equal to mu for females. There is a difference in the average score, test scores for those two populations. And just to confirm that, I'm going to go over to the significance, the probability I would be wrong if I reject the null hypothesis, and it's less than 5%. So my p-value, my probability that I would get this extreme a difference between the two means would occur less than 5% of the time if the null hypothesis were true. So therefore, I can reject the null hypothesis here because I'm satisfied that the chances I'd be wrong is small enough. Okay, so there is another example of this where the Levine's test of equality of variance, the next one comes up with significance less than 0.05, so you would use the bottom line, but you can go ahead and play around with that. That's basically the way that I would use this. The one other situation that we would run into with the t-test is when we have paired samples. And I'm going to open, that's a paired sample t-test right here. I'm going to open that value, right now. I'm going to say open data, and I'm going to say paired samples, and I'm going to say open, and open that. And in this case, paired samples are very frequently when you measure the same subject twice. Let's say we take 9 people, a sample of 9 people, and we want to test whether a drug works or does not work, say a blood pressure medication. And these numbers may be, for instance, reduction in blood pressure, for instance. And we want to know whether the placebo, the amount that the drug reduced blood pressure is different than the amount that the placebo reduced blood pressure, or if there's no difference between the two of them. So we're looking for the difference between these two. So this is very convenient. This is a great way to do a study because, for instance, if I just did placebo and drug with 9 different people, it could turn out that just on a random basis, when we select subjects with this on a random basis, could be that I'm overweighted more than half of the placebo group of females, more than half of the drug group of males, or the placebo group has a lot more smokers than the drug group. There's many variables that could be confounders that when we use 2 different groups of people that we could avoid by using a paired sample. So if we're comparing this person's performance on the placebo versus the same person's performance on the drug, say took the placebo for a month, took the drug for a month, and this one took the placebo, maybe took the drug first and then for a month and then the placebo, we would randomize that. Okay, that really I'm comparing each person to themselves. So I would eliminate that these extra unknown, extra confounding variables. So really what I'm looking for here is the difference between the two of those. So in this case, the difference is 0. There's no difference between them. In this case, the difference is 2, 4, -3, 2, -1, 6, 1, 3. The differences are what I'm interested in here, right? And the differences, if I take the differences, the average, if there's no difference between the placebo and the drug, I would expect the average difference to be equal to 0. So basically what we wind up doing is a single sample t-test for just the differences, not the numbers themselves, just the differences, and comparing it to 0. Just use 0 in the number that we're comparing it to. We're going to actually go to Analyze, Compare Means, in the paired samples t-test. And in this case, SPSS is going to wait for me to move both variables in here. I'm going to move placebo in there and drug values for each for the same person. And then I'm going to click OK and take a look at our output table. And SPSS is going to run what's basically the same as a single sample t-test, comparing the mean difference to 0. So in this case, the mean difference between placebo and drug was 1.56, the average. The standard deviation with standard error was this, and the t-value was 1.730. Well, that's a pretty small value. Even if this were a giant sample, we would need to exceed 1.96, right? And for 8 degrees of freedom, we would need to exceed 2.3, if I remember correctly, right? So we don't exceed our critical value with t. And to back that up, our p-value of significance is not less than 0.05. So there's 12% chance that we could get this big a difference between the placebo and drug, even when there's no difference between the two of them. In other words, not less than 5% chance I'd be wrong if I reject the null hypothesis. So the low t-score and the higher than 0.05 p-value or significance leads me to fail to reject the null hypothesis. Okay, so let me relax for a second, give you guys a chance to gather your thoughts. Do you have a question about that? I'm going to open up something else in the meantime. I'm going to open up this data file, NC birth 800. This is a sample, random sample of 800 births in North Carolina in some, oh, it's already open. Okay, here's the data set. So I don't see any chatting going on there, and I don't see any insecurities or questions and stuff like that. So I just want to do this, do a t-test one more time. And in this case, I'm going to look for a numerical variable. So for instance, the birth weight of these infants, these 800, there might have been 50,000 births in North Carolina during the course of this year. We have 800, a big sample of 800 of them. And I'm going to take a look at the weight of the infant at birth in ounces or in grams. I don't really care which one I'm going to use right now. But I'm curious to see, is there a difference in the average weight, birth weight of babies for mothers who were married versus who were not married? If I look at my variable view, if I look at marital status, one represents married, 2 represents not married. It doesn't say have a partner, doesn't say if they're partner, not a partner, doesn't say if they're single, doesn't say if they're divorced or anything like that, just married or not married. Only 2 values, hence a t-test. I compare the mean birth weight for married women versus the mean birth weight for not married women. Had I had other groups, 3 equals divorced, 4 equals separated, then I would be comparing 4 means and I would use analysis of variance instead of the t-test. But for our purposes right now, we're going to use the t-test. Okay, so I'm going to go back here. So let's go ahead and run this t-test, compare them. So my null hypothesis, what's my null hypothesis? My null hypothesis is, and I think I got room here, I can write this on here. My null hypothesis is mu, this is H null. The mean birth weight for married women is the same as the mean birth weight for unmarried women. Or my alternative hypothesis is the mean birth weight for married women does not equal the mean birth weight for unmarried women. So we want to know, can I reject this null hypothesis and accept this alternative hypothesis? So I'm going to go back here. I'm not going to, this is called a two-sided hypothesis. We have so little time here. I don't want to confuse the issue by introducing this idea of single-sided and double-sided, just so you know, if I had a reason to believe that this could only be possible in one direction, that married women the mean for married women the birth weight, the average birth weight of married women could only be greater than the mean birth weight, and physically couldn't be smaller than the mean birth weight, I could propose a hypothesis like this, like greater than or equal to, and then the alternative would have to be, less than or equal to, and the alternative would be greater than, right? So I could propose a hypothesis like this. The only trouble with that is I would have to have a good reason for doing it single-sided, number one. And number two, this is a more conservative test. So for the most part, even when you have an inkling you could do this, you usually wind up doing a two-sided test just like this. Doesn't make any assumptions about which of the two groups is greater than the other, just concerns itself with, are the means different, or do I have enough evidence to say that the means are truly different, or should I just not say that? Okay. So I'm going to go ahead and do this. So I'm going to say analyze, and I'm going to go into compare means. And what do you think? It's one single sample, independent sample, or paired sample? Right? I think I'm going to have to go into independent sample, two groups, married women and single women. Let me get this out of the way. So let's see. What I'm interested in for the mean, the test variable, is the weight of the child. I'm going to use ounces. They're a little bit easier to work with, smaller number. And the grouping variable is going to be the marital status of the mother. Here's the mother's marital status. I'm going to move it in here. And I seem to remember that it wasn't 0 and 1. It was 1 and 2, I think. Pretty sure it was 1 and 2. So I'm going to say click continue, and I'm going to go ahead and run my t-test. Okay, let's go. And let's see what my output looks like. I think I flashed it away there. There we go. Okay, so the mean birth weight for married women, if it's married women, there are 537 of them, is 119.57. The mean birth weight for unmarried women was 109.85. And the question is, are those two numbers far enough apart that I can take the standard error, combined standard error, and the standard deviations are very similar, combined standard error and combined standard deviation, calculate a standard error, and how many standard errors apart are they? That's my t-score. X bar 1 minus X bar 2 over the standard error. That's the way we calculate it manually and come up with a t-test. And in fact, we have a t-test result. And let's see, do I want to use the top line or the bottom line? Well, Levine's test for quality of variances. We're assuming the top unless this is less than 0.05. So it isn't less than 0.05, so I stick with the top, right? So I stick with the top, and the t-score is 5.8 for many, many degrees of freedom for a really big sample size, right? So 800 minus the two groups, minus 2. So it's t-score is 5.8. So that certainly is going to be bigger than our critical value of t. And in fact, what's the probability that I would get this big a difference in the two means for these groups if the null hypothesis were true, that the means were equal? Well, the probability that would occur is less than, well, it's not really 0. It's less than 0.001, less than 0.1% is the probability of that occurring. So since this is well less than 0.05, I can reject the null hypothesis and accept the alternative hypothesis. If I didn't have the evidence for doing that, if that came out to be greater than 0.05, that's significance, I would not have said I accept the null hypothesis. We never say that. We only say we fail to reject, right? So when we fail to reject, doesn't mean we've proved the null hypothesis. Only means that we don't have enough evidence to reject the null hypothesis and accept the alternative hypothesis. Okay, so I think we beat this to death, right? Are we okay with this? How do you guys feel about that? Are you more comfortable than when you tuned in tonight? I'm going to wait for a response just to make sure you guys are still alive out there, and you haven't been a little. Okay, little is a start, right? Little doesn't hurt. Great things were done a little at a time. A bit. Okay, good. I'm glad to hear that. Perhaps this will give you a little more confidence in doing the homework assignment on the t-test. I don't need the output for this right now. Okay, so the next thing I want to discuss is analysis of variance. And I think, let's see if I have a decent, I'm going to open up this one, high school, whatever, high school athletes, I think it is. High school female athletes. I'm going to open this file up. Oh, God, I double clicked it again. Is SPSS going to do the same thing to me? I don't know. So I'm going to go to SPSS, and I'm going to open it from SPSS. I'm going to say File. Oh, no, I'm not in SPSS. I'm going to say File, Open, Data. I'm going to navigate to there, and let's see, Desktop, Data Files. I think it's Data Files or Data Files 2. Control Heights, I don't think that's it. I think it's in the other folder. Oh, look at it, here it comes. Did it open it? No, that's still the other file. Okay, let's see, Data Files 2. So high school female athletes, I'm going to open up that one. Okay, female athletes are in the news these days, right? The soccer team's doing pretty well. And did they play today? They played yesterday. Probably take a day. They probably won't be playing for a couple of days, I don't think. Okay, so here is a data set of information about female athletes. So here's this is named nominal variable, sport. Notice that it has the symbol for nominal variables. Identifying the sport as aerobic or non-aerobic, the age of the participant, the height, the weight, the body fat, the BMI, number of sit-ups they can do, so on and so forth. I'm looking for another categorical variable here. Yeah, I don't see one. I don't see one that contains 3 variables. Non-aerobic, aerobic. This is not going to be a good data set for us. I don't have a categorical variable that has 3 values. I'm going to go back to this. So let's see. Grams, low bat, cream, ethnicity of the mother, race of the mother. Okay, race of the mother. Let's see what race of the mother is. So the race of the mother can have the values white, black, other non-white, American, Indian, Chinese, Japanese, Hawaiian, Filipino, and other Asian Pacific Islander. It can have 8 different values. There's 8 different ethnicities that are represented here. So I want to compare the means of all these different ethnic groups to see if I can identify ethnic groups where the mean birth weight for the baby is significantly different. In other words, I can reject the null hypothesis that the mean birth weights are the same. So what's my null hypothesis going to be for this kind of test? Something that I'm going to use the test analysis of variance for, right? I'm using an analysis of variance because, let me open up a piece of paper. I'm using analysis of variance because I'm comparing the mean to ethnic group 1 to the mean to ethnic group 2 to the mean to ethnic group 3 to the mean to ethnic group 4, et cetera, et cetera. I think there's 8 groups altogether, mean for ethnic group 8. Right? And comparing all of them and saying my null hypothesis is that they're all 8 are equal. And my alternative hypothesis is that at least 2 of the means are different. Not all of them have to be different, but at least 2 of the means are different, are not equal, right? So that is my test. That's what analysis of variance is going to do for me. So analysis of variance is 2 steps. Analysis of variance, in the first step, you determine whether you can reject this null hypothesis and accept the alternative hypothesis. If you can do that, if you can reject the null hypothesis, accept the alternative hypothesis, well, then you go from analysis of variance to post hoc tests. And post hoc means after the fact. So it's your opportunity that now you've shown that at least 2 of the means are different to see which of the means are different from one another with less than 5% chance of being wrong if you say that they're different. Okay, so you would only run the post hoc test after you run the analysis of variance, and that tells you, and that has told you that you can reject the null hypothesis. So we're going to do it for this particular data set. Okay, so here we go. So I'm going to go back to data view just for the hell of it. You don't have to, you can do it from the output view. I'm going to say analyze. What am I doing here? Where is analysis of variance? Well, I'm still comparing means, even though the name is analysis of variance. It's comparing means. It's using the variability between the means of each group and the variability within each group to see if they're different enough to determine if you can reject the null hypothesis. So analysis of variance is a comparison of means, really. So I would go into compare means, and sure enough, there it is, one-way analysis of variance. So in this case, I'm going to put, what am I comparing now? I'm comparing the birth weight of the child, and I'm breaking it up into groups, which include the race of the mother, which is 8 groups. Okay, so notice that in post hoc, I have nothing checked because I'm not going to run the post hoc test until I know I can reject the initial null hypothesis that not all of the means are the same. So I'm going to click OK. SPSS is going to run this analysis for us and come up with a table. Okay, warning, post hoc not performed for weight of child because at least one group has fewer than 2 cases. Okay, so we have a little bit of a problem. One of the groups has fewer than 2 cases, and we could actually look up to see what that one is, and we could remove it. Okay, so degrees of freedoms. So actually used only between groups. I think we'd only use 6 of the groups. So the significance is less than 0.05. You know what I'm going to do? I'm going to go back here. And I'm going to say analyze, descriptive statistics, explore. And I'm going to do this calculation for race of the mother. Oh, hang on a second. The factor is going to be race of the mother. And the weight of the child is going to be our statistic. And I'm going to say click OK. And I'm going to see which of these groups have very few values. So let's see. So white, black, American Indian, Chinese, and Filipino have very few people in the group, in these groups. So I am going to remove them and just have white, black, American Indian, and Asian Pacific Islander. Let me see if I can do that by just going in here. Okay, and I want to go to variable view, and I'm going to go into race of the mother, and I am going to remove other non-white. Apparently there were none in there. And what were the ones that were a problem? I forgot already. Let's see. Chinese and Filipino. I'm going to remove that. And I'm going to remove Filipino. And let's see if it will only analyze the remaining ones for me. White, black, American Indian, and other. Okay, we're going to take out Hawaiian and Japanese. Apparently there weren't any Japanese women in here, so I'm just going to work with those variables. Let's see if it'll work for me now, or if I actually have to remove those from the data set rather than just not define them. Analyze, compare means, one-way analysis of variance. Now we only have 4 groups in race of the mother. I'm going to click OK. See if we still get that warning. Oh, we didn't get that warning this time. Okay, good. So let's see what we wound up with here. So we wound up with, let's see. Okay, here's box plots. Oh no, we did that. This gave me for the whole, this was descriptive statistics for everything. I'm going to analyze, compare means, one-way analysis of variance, weight of the child, race of the mother. Let's run this again. And let's see, the child, at least one group has fewer than, well, it analyzed it for the other groups, the groups that it had data for. Well, in fact, in this case, I'm going to go ahead with the analysis. In this case, the F score, the analysis of variance score, tells me that there's less than 5% chance that I would be wrong if I reject the null hypothesis and say that there is no difference, that all of these means are equal. That I can go ahead and reject the null hypothesis. I can reject the null hypothesis that all of these means are equal to one another. Now I can go up and do my post hoc test. Analyze. I'm going to go into compare means and one-way analysis of variance. And now this time I'm going to turn on post hoc test. And I'm going to choose Bonferroni, for instance. Okay, let's see if it actually does it for me. Again, I may have a little bit of a problem because it's not happy with the data set. Yeah, it didn't bother to do the post hoc test for me. So you know what I'm going to do? I'm going to use a different variable. There's another variable in here, which is ethnicity of the mother, which only has 3 groups, I think. Let's see what they are. It has, see, SPSS, if you try and violate the rules, SPSS will straighten you out occasionally. Ethnicity of the mother has 4 values: white, black, Hispanic, and other. Okay, so I'm going to see if there's enough people in each of these groups to do my analysis. I'm going to say analyze, compare means, one-way analysis of variance, and this time, instead of race of the mother, I'll use the variable ethnicity of the mother. I'm going to say, okay, and let's see what my analysis of variance comes out to be. My analysis of variance comes out to be 8.22. My significance is less than 0.05, so I can reject the null hypothesis that all the means are equal and say that there's at least 2 means that are not equal to one another. Not all of the means are necessarily equal to different from one another, but at least 2 of the means I can say with the level of certainty I want, alpha is less than 0.05, that at least 2 of the means are different from one another. Now the question becomes, which 2 means? So at this point, you would go up to analyze, and you may have noticed that it really did it already. I go up to analyze, compare means, one-way analysis of variance, and go into post hoc and check off one of the post hoc tests. Now, these are usually applied in slightly different circumstances. Some are better for certain application, but Bonferroni and Tukey are 2 of the most commonly used. You could use either one of these 2, and they are relatively conservative methods of calculating the post hoc test. Post hoc meaning after you've proven that at least 2 of them are different, now you can go ahead and run the post hoc test to determine which ones are different. So I'm going to click continue and OK and have it run the post hoc test as well. So it repeats the analysis of variance and with the same result, and then it comes up with our comparison. So each one of these boxes compares whites to black, and the significance is 0.000. So our null hypothesis is that they're equal. The significance being less than 0.05 allows us to reject that null hypothesis and say, oh, the mean birth weight for whites is different from the mean birth weight for blacks. The mean birth weight for whites versus Hispanic, well, that's not less than 0.05, so I can't reject that null hypothesis. I haven't proven that they're different. Whites versus Hispanic is different. How about whites versus other? Whites versus other, I haven't proved either. That's not less than 0.05. Well, now SPSS goes through every possible permutation here. Well, what about blacks versus blacks versus whites? We just did that up here. Got the same result, right? That we can reject the null hypothesis. How about blacks versus Hispanics? We haven't done that yet. Can we? Yes, it's less than 0.05. We can say we can reject the null hypothesis that those 2 means are equal and say that the mean birth weight for black infants in this study are different from the birth from Hispanic babies in this study. And how about blacks versus other? Well, that one, not quite. We haven't quite proved it. It's not less than 0.05. So we failed to reject the null hypothesis. Very frequently, if you're doing a real study, that might be sufficient for you to to feel strongly that that might be true, and you can reject the null hypothesis. You know, in real life, you know, it's such an arbitrary level, 0.05, that you might still publish papers saying that, well, we have got this level of confidence that that there's a difference in the birth weight for these 2 groups. So that's how we would use analysis of variance to do the same thing we do with a t-test, except do it for situations where we have more than 2 groups that we're comparing. T-test is 2 groups. Analysis of variance is 3 or more groups. Okay, so so we've dealt with a couple of different situations where we have variables, a categorical variable, and a numerical variable together, and we actually do this. And we actually create a null hypothesis and calculate these likelihoods. So now let's take a look at another situation. And again, we have some, I think you have some videos that should help you out on this as well on Blackboard. But now we're going to take a look at another kind of situation where we have two categorical variables. And those two categorical variables, I'm going to open up a new data set. Let's see. Let's see what I got open already. If I can work with something I got open already. Let's see. Let's see. High school female athletes. Let's continue to use this one. Okay, so I'm going to take a look at a couple of nominal or categorical variables. I'm going to look at the smoking status of the mother and whether the baby was born prematurely. So the smoking status of the mother, how many values do we have for that? We have two values. The mother did not smoke or the mother did smoke during pregnancy. And for the whether or not the child was born prematurely, we have how many values we have there? Yes, 0 is the infant was not premature, 1 is the infant was premature. So I am going to go into, I'm going to go back to my data view so I can look at it. I'm going to say analyze, and since they're categorical variables, in other words, yes or no, premature, yes or no, and mother smoked, yes or no, right? Those two categorical variables, I can organize those into a contingency table. Remember, similar to what we were doing with our diagnostic test. In the rows, I can put the exposure. In other words, in the rows, could be top row could be didn't smoke or did smoke, and the bottom row could be smoke or not smoke for the rows. And in the columns, premature baby versus not premature baby. So I'm going to give that a try, except that is a contingency table. And that's hidden away up here in descriptive statistics. We're going to go to descriptive statistics, crosstabs. So it forms kind of a crosstabs table or contingency table. I'm going to click on that. And I'm going to say that the variables, okay, are smoke during pregnancy, in the rows, the exposure, and in the columns, whether or not the infant was premature. Okay, I'm going to put that in there. And over here, I have a number of boxes I can click here. In statistics, it's going to calculate a chi-square statistic. It's going to calculate odds, risk, and relative risk. I'm not going to do those right now. I'm going to skip that. I'm just going to go into cells. And I'm going to tell it, just give me the observed values. I'm going to click continue, and I'm going to click OK. And it's going to produce our contingency table. It's going to take these 800 women and put them into a contingency table. And 798 women, apparently there's some missing data there. Well, let's take a look at what we have. Well, how many mothers did not smoke during pregnancy? 684. How many mothers did smoke during pregnancy? 114. Okay, so out of the 684, how many women had premature infants out of that group? 78. Out of 114, how many women in that group had premature infants? Well, 15. Okay, well, that's interesting. Wow. Okay, so let's make that a little clearer. Let's get percentages by rows. Okay, so I'm going to go up here to analyze. I'm going to go up to descriptive statistics and crosstabs. And I'm going to go back into the cells, and I'm going to check off expected values, not expected values, percentages by rows. I'm going to click continue and say OK. Okay, so now I'm going to take a look at this. Among the women who did not smoke, 11.4% had premature infants. Among the women who did smoke, 13% had infants who were premature. Is that big enough difference for me to say with any kind of certainty that that there's an association between smoking and premature birth? Well, that's where chi-square comes. That's where chi-square and odds ratio and relative risk come in to help us out. Okay, we want to know whether we would expect that this case would not be unusual, and if it is unusual, reject the null hypothesis that there's no association. So our null hypothesis here, a little wordy, but our null hypothesis is that there's no association between smoking and premature birth. Okay, so that's our alternative hypothesis is that there is an association. So we're going to try and reject our null hypothesis, accept our alternative hypothesis. And the way we're going to do that is we're going to perform our calculation for analysis of variance. In the videos, we did this online by hand. In fact, I want to go over one of the problems here because I had a couple of people ask me a question about homework 7, one of the problems on homework 7. I want to go over that problem. But for right now, let's do this. So I'm going to go up here to Analyze, Descriptive Statistics, Crosstabs. Except this time, I'm going to ask SPSS to calculate the chi-square value and to calculate the risk for me. That's going to give me an odds ratio, and it's going to give me the chi-square value. And I'm going to click OK. So in addition to our chi-square value, our crosstabs table now, we're going to get these other statistics. Okay, so let's see. Chi-square, our Pearson's chi-square value is 0.292. And our probability that we would get this big a difference in our table if we were to assume that the null hypothesis is true, the probability that we'd be wrong if we reject the null hypothesis is almost 60%. It's not less than 0.05. So we fail to reject the null hypothesis. These results are not different enough for this size sample for us to be 95% certain, or less than 5% chance of being wrong if we reject the null hypothesis. Similarly, the odds ratio, the probability that you would have a premature birth, that you have a premature birth if you smoke, is 17% more, 1.17 times the for women who smoke versus women who didn't smoke. However, that's nice. That's nice that we calculated that difference between these two percentages. But in fact, if I look more carefully, the confidence interval for this is 0.65 to 2.12. In other words, we're 95% sure the true odds ratio is between 0.65 and 2.1. Well, what does that tell us? That tells us that it could be 1. Odds ratio 1 means that there's no difference in the odds of having a premature baby if you smoke versus if you don't smoke. So in this instance, we failed to reject the null hypothesis for 2 reasons. 1, because our chi-square value wasn't big enough, and 2, because our confidence interval for our odds ratio did not exclude the value 1, the value we would get if the odds for both groups, the exposed smokers and non-smokers, was the same. Okay, let me see if I can do one more of these, just to see if I can't catch one where it actually works. Go to crosstabs. This time I'm going to take out smoked. And how about marital status? Let's see if marital status makes a difference. Okay, let's see. Let's take a look at marital status. Well, let's take a look at marital status here now. Marital status here is 8.9% of the women who were married had premature births. 17% of the women who were unmarried had premature births. Wow, that's a big difference from the last one, right? Okay, so let's take a look at what our chi-square value is. Our chi-square value is 11.475 with 1 degree of freedom. When it's a 2x2 table, it's number of rows minus 1, number of columns minus 1, 2 minus 1 is 1, 2 minus 1 is 1, 1 times 1 is 1, so 1 degree of freedom. If we went to the table for chi-square, we would know critical value of chi-square is 3.84 for 1 degree of freedom. And in fact, we've exceeded the critical value. We can reject the null hypothesis that there's no association between marital status and premature birth. And in fact, our p-value, our significance, is well below 0.05. We have justification here for rejecting the null hypothesis that there's no association between marital status and premature birth, and accepting the alternative hypothesis that there is an association. How about our odds ratio? Well, women that were not married had a 2.1, had a double the odds of having a premature birth versus women who were married, right? And to boot, the confidence interval tells us that's the value we got for this sample of women, but the confidence interval tells us for all of the women, the entire population, the confidence interval for the true odds ratio for the entire populations would have been 1.36 to 3.2. It excludes 1. It tells us that we're 95% sure it's not 1. In other words, the odds for the ratio of the odds for women versus the odds for married versus odds for not married, we're 95% certain is outside of our 95% confidence interval. In other words, we're 95% sure that it's not 1, not equal for the two groups. Okay, so I hear stunned silence. When I say I hear stunned silence, I don't hear anything, right? I just see that I don't see any comments there, no questions. Can I assume everybody understands this 100%? There's a lot to absorb. Okay, great. Well, I'm gonna record this, of course, and I'll put it back up again. I just want to go over that homework assignment that a couple of people asked me about, assignment number 7. And I can do this again. We have 2 weeks left. We have not even 2 weeks. We have less than 2 weeks left of this semester. I'll be posting by tomorrow night, late tomorrow night, I'll be posting exam 2, which includes the t-test, analysis of variance, chi-squared will concentrate on those elements. And I'll be able to give you from when it's posted late tomorrow evening until, say, Sunday, right? You have a decent amount of time to work on it. You'll get 2 attempts at it again. After the first attempt, it'll self-grade. You'll be able to see which ones you got wrong, and then you have a chance to redo it. Okay, so you get another shot at it. So I'm hoping that'll give you a chance to kind of like, figure it out and work on it and stuff like that. And yeah, I'll have another review between now and Sunday night, maybe on Saturday or something like that, right? Saturday morning or something like that. So we'll get together again. Hopefully, if you post questions on Blackboard for the review session, I'll go over them. But I want to go over this one problem in the homework, because definitely I got a couple of questions on it. Okay, but you really need to buckle down. This 5-week course is brutal. I understand that, but man, it just the time just flies. It's very, very unforgiving. It's not my idea. I would rather have 8 weeks with you people than have 5 weeks. I wasn't able to do the post hoc. Okay, I'm not sure. What you mean by that? When you say you weren't able to do the post hoc, it said that it doesn't take sample over. It doesn't take sample over. It sounds like you might have. Did you pay for the version of SPSS you're using? Because there are versions of SPSS that are very limited. They won't analyze more than 50. It might be a problem where your license is not correctly. You had the one from CUNY. Oh, you mean School of Public Health, the free one? I don't understand why it would tell you that. That's a new one on me, because that would suggest the license is expired, and it kind of defaulted to a version of it that won't take large sample sets. Like won't take more than, say, 20 variables and 50 subjects. Is it possible that that's what's happening? Maybe we need to check with. What I can do is I can reduce the data set to 50, so that you can still do the test. Wow, that's a new one on me. I'm gonna have to contact the tech group and see if there is an issue with that, or maybe their license ran out. Maybe the license or the version that they're letting you download has run out. Because my version I'm using on here is also downloaded from School of Public Health. So I don't know why it would be doing that to you. So if one of you could take a screenshot of the message, exact message, and email it to me, I'd appreciate it, because that way I can pass it on to the tech group and I can resolve that. I'm glad you brought that up now. Because I want to make sure that's resolved before I give you a problem on the exam, to make sure it's one that you can work on with the exam, so you're not discouraged by that. We have enough obstacles that we don't need another obstacle. Okay, let me go into BIOS610. Let me go into assignments. But yours should work exactly the way mine works, because it's the same source, came from the same place, unless the PC version and the Mac version have different license situations. I don't think that's true, though. Okay, so let me go in here. Okay, and I'm going to say begin. And it is, I may open Excel to do this. Okay, here we go. Now, paper, null and alternative hypothesis. Your null hypothesis test comparing the exposure for air versus paper is there's no association between drying and illness. There is an association between drying choice and illness. That sounds pretty legit to me, right? That sounds true to me. Okay, what is your estimate of the prevalence or incidence of illness in this population? Well, out of 98 people in this population, 29 of them have became ill, right, after using whatever method in the bathroom. Okay, so boy, this pretty virulent disease that's coming off of these towels or these blowers in this bathroom. So 29 out of 98 people got ill. So the incidence is 29.2959, et cetera, et cetera. I'm going to use Excel. I'm going to use Excel so I don't have to keep repeating these numbers. It's going to be easier, I think, in the long time. Cholesterol measure, yes, cholesterol measurements go into the top box, and the education group goes into the lower box, the factors box, because education is a categorical variable. At least I think. I don't know which problem you're referring to, but it sure sounds like that. It certainly does sound like that to me. Okay, so I am going to go here. I'm going to say, let's blow this up to 250. So we can see, and I'm going to go over here and I'm going to fill this in. I think I actually have it here somewhere, but I'm just going to fill this in here. 27 and 10 and 42. And this is 46. That looks right. And this is, let's see, that's 52. That looks right. Okay, and the total here is 98. That looks right. And this is 29. And this is 69. And 69 and 29 is 98. Yeah. Okay, so prevalence. The prevalence is going to be equal to, 29 divided by 98. Prevalence in this population is going to be approximated by this. Okay, so now let's say that this is our expected value. These are our observed values. These are our observed values. And I'm going to make up a new table. And just so we're clear on this, this is the people that got sick. This is the people that didn't get sick. This is the people that were exposed, I think. Am I right about that? And these are the people, well, it's actually paper and whatever. Paper and hot air. Paper versus hot air. Okay, actually put the hot air ones in there because they thought they were going to be more sanitary because you don't touch anything. But turns out you blow stuff all over the place. Who knows, right? So okay, so I'm going to just highlight these boxes here. I'm not going to leave it the way it is. So now I'm going to create a new table for expected values. Okay, down here, and I'm going to take a look at this. So I'm going to take the totals here. 46, 52, and 98. Okay, that's the number of people that use paper towels and so on and so forth. And this is paper. Oops. Expected values. I should have moved this down. Okay, so this is paper. And this is hot air. Okay, so let's see. Out of, I gotta move this over a little bit too. Put it there. Okay, so how many people would we expect to get sick if everybody, whether you were exposed, whether you used paper or you used hot air? how many people would I expect to get sick if I used paper, if everybody got sick at the rate of about 29.5%? Well, this value in here is going to be equal to the 46 people times the likelihood that you would get sick if there's no difference between the two populations. So I would expect that to be 13.6. Well, okay, so now let's do the same thing for people that use hot air. I would, those people that use hot air, this is going to be equal to 52 times the probability that you would expect to get sick if there's no difference between you and the people that use paper, just the general population. And the difference between these is going to be equal to 46 minus this, because it's got to add up to 46 people. And this is going to be equal to 52 minus this number. Okay, and if I add these together here, like so, surprise, surprise, it comes out to 29. If I add these together here, parentheses, surprise, surprise, it's going to come out to be 69 here also. But this is the way I would have expected them to be distributed. So instead of getting 13 as I would have expected, if there's no difference between using hot air and paper, I got 19 real people that got sick. Instead of getting 15 people get sick if they used hot air, I only got 10. I got fewer than I would have expected. So sure looking like paper is the worst choice here, isn't it? So we're going to calculate a chi-square value. And if you guys remember, the chi-square value is equal to, chi-square is equal to, or you can use it as just the x with a 2, with a 2. The chi-square value is equal to, what is that equal to? It's equal to the observed values minus the expected values squared. Okay, squared, it's tough for me to put the superscript in there right now. Squared divided by the expected values. Okay, I won't go into the whole thing. If you want to look at the video again, you can. Arrangements with the 2 boxes. Okay. So far I've done something that has helped out, I hope. Okay, good. I want to finish the problem anyway for everybody else that's looking over on this. Okay, so the observed value minus expected squared over the expected value. Well, you're going to do that for each box. So normally there would be, I can't draw it in easily, there would be a summation here from n equals 1 to n equals 4 for each of the 4 boxes in this 2x2 table. So I'm going to go ahead and do that for each one of these 4 boxes. So the first box is going to be equal to the observed value minus the expected value squared, and squared, I got to put in a caret here. Where is it? Let's see, where is it on this? It's got to be in the same place on this keyboard as everywhere. There it is. Okay, squared divided by the expected value. So what I get? I get 2.13. Now I'm going to do the same thing for the observed value and for the hot air observed value and expected value. Actually, I can cheat on that, right? I can just copy it down. Since they're both in the same position, I can actually copy it down and it'll do it for me. So now I'm going to do it. I'm going to go across from there to the right, and it'll do it again for me, except it's going to do it for this, the observed value minus the expected value divided by the expected value. For this, if I copy across, copy the formula across, and then again down. So all I did here would be, if I did this one, it would be doing the same thing as we did here. I would say equals sign, and then I would put in, click into the, for this one, observed value of 42 minus the expect value 36.61, then put the caret and square it, divided by the expected value, which is 36, and I would get this number. Just I did a shortcut. So I'm going to add these together. Equals the sum of all of these, summation of all of these values. And my chi-square value is 5.7. Now I would go to the chi-square table. Grusty? I think it's a Grusty. Wait, can I find it? Come on, help me out here. Let's see. Chi-square table, where is it? I don't see it. How about if I put this in the other way? How about if I put in a Grusty? I use this from an old textbook that I like. So, yeah. Oh, did I just see it? How about if I just say chi-square table? You know, I actually think I have it on Blackboard behind me. Chi-square table, PDF. How about that? Wow, I'm striking out here, aren't I? Oh, here it is. I knew I'd get it eventually. Okay, so here's a chi-square table. I'll blow this up a little bit. So what is the critical value for a probability, a critical value for 5%, alpha equals 5%, for 1 degree of freedom? Remember, it's that rows minus 1 times tables minus 1. 2 minus 1 is 1. 2 minus 1 is 1. 1 times 1 is the degrees of freedom of 1. And the critical value is 3.84. That's the value that I have to exceed to reject my null hypothesis. And in fact, I have exceeded that value, so I can go ahead and reject my null hypothesis. We can do this in SPSS also. I think you might even have in the data set that goes along with this, I think you might have the, actually I just wanted to mention one other thing, that the odds ratio here, the relative risk, right, is 19 over 46 divided by 10 over 52. And the odds ratio is 19 over 27 divided by 10 over 42. So if there's no difference between the odds of getting the disease or not getting the disease with paper or hot air, you would expect the ratio of the odds for paper and hot air to be equal to 1. And if it's not equal to 1, and the confidence interval for that odds ratio excludes 1, doesn't include 1, you can reject the null hypothesis that the odds ratio is equal to 1 and accept the alternative that it's not equal to 1, which means that the odds are different for the two groups. Okay, let me. So I think we closed. I closed that off. I wanted to do this again in. I think. Let's see. Let me go back another step to the assignment page. There we go. And here is hot versus paper. There's the Excel version of this file. So I'm going to save this on my desktop. Did it go to my desktop? It didn't really give me an option. There it is. Okay, I'll save it on my desktop. And I'm going to do this in SPSS now. I'm going to repeat this problem in SPSS. Let me get SPSS here. And I'm going to say, okay, I'm going to open the file and say, they open data, navigate to my desktop, look for that file on my desktop. Here it is, hot air versus paper. Open it up. Okay, and now I am going to ill and not ill, I guess is what I use. But what are the numbers there? Let me take a look at the variable here just for the hell of it. It's all 1s and 2s. Okay, value label. I'm going to go to analyze, and again, chi-square is going to be under descriptive statistics crosstabs. You're going to make a cross, basically you're making crosstabs, right? Or a 2x2 table, or it could be more than a 2x2 table. I'm going to put the exposure in the rows, which is the kind of hand dryer used. And I'm going to put the outcome, whether the person got ill or not, in the columns. And I'm going to ask it to calculate for me the chi-square and the odds ratio, risk. I'm going to click continue. And I'm going to say, and then cells, I'm going to ask it to calculate the observed values and the percentages by rows. Now let's see what I get out of this thing, out of my output table. I'm accelerating this so that we can get done with it. Okay, so let's see what we get. Okay, so first of all, look, here is our observed values. If I wanted, I could have checked off also expected values, in which case in each box along with the 19, we would have put the expected values, presumably the same as we calculated it. So our 43% of the people who used the paper got ill, while only 19% of the people who used the hot air got ill. So my relative risk is 41% over 19%, or almost 2 to 1. Our odds ratio is 19 over 27, right? 19 over 27 is approximately 0.66. And hot air is 10 over 42, which is approximately 1/4. So 0.66 over 1/4 is about almost 2 or 3 to 1, right? So if I go down here, I see here's my chi-square value, right? Which we know is greater than 0.3, 0.84, so we can reject our null hypothesis that there's no association, and accept the alternative, there is an association between whether you use paper or hot air and whether or not you got ill, right? And I can also confirm that by looking here to the significance and see that the probability that we would get this extreme a difference between the rate of illness in these two groups, if the null hypothesis were true, meaning there's no association, that the chances of that occurring is less than 2%, well under our 5% threshold for rejecting the null hypothesis. So this being less than 0.05 and this being greater than our critical value of chi-square, both are indications we can reject the null hypothesis. In the meantime, people that use paper, the odds for people that use paper versus hot air, the odds were 2.9 times as great that they would get ill versus people that use hot air. And not only that, but in addition to that, my confidence interval for the true value of the odds ratio is 1.2 to 7.3, meaning it's not 1. We're 95% sure that 1 is outside of this interval. So we're 95% sure that the odds for the two groups are not equal. More evidence you can reject the null hypothesis that there's no association between the two groups. Okay, and I'm losing my voice at this stage. So that would be a good time to call it a night. So I will convert this, get it uploaded as quickly as possible. And I hope this helped a bit. So work on the homeworks, please. Go to our homework, get as high a score as possible. One of the homeworks, one of the more recent homeworks in homework 1, you have to wait for me to grade them, to go through them and grade them, because it's that kind of submission will not auto grade. So I'll take care of that. But most of the other stuff will auto grade. So you get a look right away and you can go back and try again. Any of the homework from previous, so you can go back and try to get an improved grade. Okay, so that'll help you out a bit. Now, please, on the new exam, okay, you got like 4 or 5 days, at least 4 days, where you're going to have the exam available to you. Give at least one attempt so you get a chance to look at the problems. Take a few notes so you know if you can mull it over, go to Blackboard, maybe play a video or something like that, help you out. So don't, I noticed some people waited so late to do the exam that they shut themselves out of the opportunity to do it a second time, right? So that's really silly, isn't it? You really should. That first attempt is almost a freebie, right? Because if you take the second attempt, that the higher grade is the one that's going to count. So make sure you take advantage of it. Don't let that opportunity slip away.